All right, we ready to get started? Yeah. All right. So welcome to a primer on functional programming. My name is Sarah Withee. You're welcome to tweet along if you like, if you're into that kind of thing. But first, I kind of want to know who's heard of functional programming. Hopefully most of you, yeah. Otherwise, you probably wouldn't know what you're really getting into, I guess. Who's done some form of functional programming that you know of? A few people. All right, that's kind of what I'm expecting. Would any of you say you are a functional programmer? One of you? All right. And who's wanted to learn about functional programming but never had the time, never really had the resources, or things like that? Okay, good. You might be my kind of crowd. So that's kind of what I was hoping for. When I went to college in the US, I ended up taking a programming languages course and did a whole program in Haskell. And then by the end, still didn't really know what functional programming was, even though that was like a thing we were supposed to learn in the course. And then just kept hearing it pop up and realized I never really understood what it meant to program functionally. So that's sort of the spawn of this talk, was sort of that research and kind of learning from that and hoping to be able to share those things. So you in the back that said you are a functional programmer, I don't know if you'll get as much out of this, but hopefully, if you leave, I won't be offended. So kind of quickly, I'm going to go over some of the functional programming concepts, and then kind of talk about why we might want to use functional programming, and then kind of take a super brief glance at like differences between functional programming languages and not functional languages, and that might be a little different than what you might think. So hello, good morning. Like I said, I'm Sarah Withee. I'm a software engineer. I've worked in a variety of different languages over the years and kind of a whole different wide variety of fields as well. I'm from Pittsburgh, Pennsylvania, which is kind of the eastern end of the country. And I'm Geeky Girl Sarah on pretty much all the things in Twitter as well. So I'll be tweeting throughout the conference too. All right, so we can dive into the basic concepts of functional programming. And the first thing I want to point out is it's really not new. I think it's kind of one of the big buzzwords that's floating around a lot of conferences and programming worlds lately, but it's really been around, most of these ideas have been around since the 50s. So it's been, a pretty solid idea for a really long time. And it's built on the ideas of Lambda calculus, which was invented in the 1930s. And I won't go over that, don't worry. It's really dense and kind of ugly, but that's where a lot of these basic ideas stemmed from. And if you get nothing else out of this whole session besides this one main point, it's called pure functions. So a pure function is a function that, when you give it a certain input, will always give you the exact same output. Which also means that pure functions don't have side effects. So you know when you run this function, it works the same way, nothing around in other areas of your code or your system are getting modified through it. So you know it's also like really accurate. By side effects, I mean different things like checking on the time, which changes obviously every second or millisecond. Anything dealing with file access, because you don't always know if files are there or not. Database access, you don't know if records have changed, or maybe your database could even just disappear. You don't know, things like that. Same for network access. You don't always know if your drives are there or they're accessible. And same for previous function calls. If one function relies on another function working and it doesn't get called in that order, then you can't really guarantee you're getting the same output, so it's not a pure function. And user input is never pure, duh. How many of you can reliably, accurately know that your users are using the program correctly? No hands. Yeah, exactly. You can't rely on user input being the same. And so, and also call by reference is never pure, because unless you absolutely know the stuff you're bringing in is the same, but you're also usually changing the state. When you do call by reference, you're changing those variables that are passed in. So that's not a pure function. And at this point, you might be thinking like, wait a minute, this sounds like nearly impossible to really write a functional program. And you're right, you pretty much cannot do it in a 100% scale. But we'll talk about it in a bit, how we can kind of work with a predominantly functional thing and deal with those weird side effects in a little while. So some examples could include a lot of math functions. So things like taking the absolute value or like the sign of a number or the square root. These always return the same values for every input you give it. So we know they're definitely pure functions. And we can do the same for a lot of like functions based on data types as well. So the length of a string is always going to be the same if your string is the same. The same if it's empty, the same if you're concatenating two strings. As long as the strings are the same, you'll always get the same result. Same for get account number from database. Okay, I'm kidding. Obviously. So that's not pure. So many things are wrong with this one. So obviously that's not pure. So to kind of recap, given a certain input, you'll always get the same output. No side effects. Anything your users do is definitely not pure. Call by reference is also not pure and is pretty much impossible, but like I said, we'll talk about that in a bit. So referential transparency is kind of a complicated term for what we say any expression can replace a function with its return value with no behavioral changes. So if it's a pure function, you can take out the function and put in a value, and everything would be the same that way. So an example of this would be if some function, always returns the value of 3, then you can basically take out that function, put in 3, and it would still work the same. I don't think anybody would ever do this, but it's an example that makes sense, kind of in a nutshell. So if we want to get a little bit more complex, if we want to do like a few more math things, if x was 30, then the sine of 30 would be 0.5, and the cosine of 60, or like 30 times 2, would be also 0.5, and so that would be 1, but we can also take out those functions and replace them with the values and still get the same thing. Pure functions are always have referential transparency, so you always know that the values and the functions can do the same thing. And as we kind of alluded to, in mathematics, all functions are transparent. But in programming, this is not true, and you can probably start to think of a few examples of where this might be. But one important one I kind of want to cover is that assignments are not transparent. And it's not really immediately obvious at first. But when you're done with this equation, so x has changed when you're done. X is not the same as what it started with. So your outside state has changed, so this is not really a pure function. But we can kind of rewrite that as sort of an add one function. So given a number, it will return, the modified change. So that's sort of the functional way to do it. And same thing if you wanted to like double a number, rather than times 2, you would just write a function that would do this for you. And because of that, functional languages usually have immutable variables, so you can't change them. Once you store a value on them, they don't change. And some languages let you kind of play with that, but so this is kind of a concept of and it's for a safety reason. So it's to make sure, your outside state doesn't change. So you hopefully, once you set it, it's always going to be the same throughout your whole program. And if you want it to change, you have to deal with it yourself. This also usually means that some functional languages have type inferences. So, if x equals 1, it can defer that x is always going to be a number or an integer, or however your language kind of picks up on that. And the pro of that is that at compile time, you can also detect some errors too. So if you set x to be a string and you're trying to multiply it by 2, at compile time, that's not going to work. You would end up erroring out when you try to run it. So it can catch things like that at runtime. Okay. Has anybody heard of Lambda functions or anonymous functions? Yeah, probably most have. And possibly some of you have even written these. And they're functions without a name. I do want to point out that lambdas can't be recursive because you usually call a function with the same name over again. But otherwise, I found there is like a weird, quirky example of a way to make a recursive Lambda function. And you can ask me about that later if you want. But the basic idea is you can't use them to do recursion, but in functional programming, you would do recursion normally. So why might you use lambdas? They can assist in higher level functions. So sometimes it's just easier to make like a simple function, like if you're doubling a number, you don't even need to almost give it a name. You can kind of pass that on to another function if you needed. You can pass arguments to another function. So instead of like calculating a value and then taking that value and passing it, you can just kind of, do it all in the same step. And usually you only do this if you call this function like once or twice. So it's just simpler to do that. An example of a lambda might be this one here. So if you have a lambda that takes in an x and then multiplies it by itself, so basically you're squaring it, and then you can print out just f. So f is kind of treated like a variable, but it's really stored as a function. And then so when you pass in 5, you would get 25 for the output of f. And doing things like this also kind of means, so x would be the argument. I've also seen some languages just say function, and then you just write it, so you don't end up having a name either. So depending on what language you work in. I forgot about all this. So functions are now values, if we think about this. So if we just have I usually have taught programming where I refer to variables as like boxes that hold some value, but now we can think of like a box that now holds a function. And because we sort of have this self-contained box, now we can pass this to other functions as well, almost as if it's a parameter. And one example of this might be, so if we had a divide function that takes two numbers and then just returns one divided by the other. And then we made another function that's just a divisor. And so it would just be a lambda function that returns a number passed in and then calls a divide function. And then you can store a variable called half that would just take, the half of something. So it would be the divisor of 2. So now half is this sort of lambda function that can just take whatever's passed in and divide it by 2. So then if you were to print out half, you would get 16 if you passed in 32. So are we all good so far? Yeah, it's a really quiet room, so I have trouble telling how you're all doing. Okay, and you may have seen some of these examples. So who's heard of map, reduce, filter, those kinds of functions? And who's possibly even used these too? So the basic idea is you have some sort of list of items, you can pass a function into it, and then it applies it to every item in the list. So just to make sure everybody's heard of these, map is a function that's in most languages nowadays. So it takes some sort of function and just applies it to every item in the list. So it's usually of some form of map, function, comma, list, or list, comma, function. An example would be if we had like an array of items, so in this case 1 through 5, and we were to square it. So squared is now the resulting list of this lambda function. So we're passing in a lambda that says take every item, multiply it by 2, and then items would be that list we're passing in. It would just apply it to everything and then return squared as a new list. And this is basically the same thing if you were to do it as a for loop. So for every item in squared, you would just append another squared item onto it. Filter is similar. So it creates a second list that has seen, or you pass in a function, and then if the item passes through that function, then it will return in the second list. So it's kind of the same thing, takes a function in the list. So in this case, if we wanted to take a list of items and find out if anything was under 5, you can just pass in a lambda that's as x less than 5. So if it's true, it will go into the new list, which is sort of, again, the same thing as another for loop. So if it's under 5, you would just append it to that list. So reduce is also a handy function. So instead of kind of applying a function to the whole list, it sort of applies the function to everything and returns one value. So it's usually some sort of computation, like if you wanted to add everything in a list, for example. So if we had another array of items, you could reduce that list by multiplying each thing together. So x and y would be, one would be kind of the recurring result so far, and then the next one would be the item getting, computed into it. And this will kind of depend on language, which one's which. It's kind of the same thing as if we were to take the product and just multiply it by each item in the list. So these two are really similar. And it kind of depends also which language you're using. So some reduce each item to the left and some reduce each item to the right. And some even have like separate functions to do this. And some it's just called reduce, and you kind of have to figure out which one it is. I saw this tweet once, which has a pretty good example of how to do this. So if you were to take a list of corn, cow, and chicken and apply the cook function to them, then you get popcorn, hamburger, and egg. And then if you were to filter on is vegetarian, then you would get back the popcorn and the egg. And then if you were to reduce them by the eat function, then you would just get the poop emoji. That's a pretty good example of how it works. So if you have any sort of operation that you need to do on an entire list, then doing it functionally usually makes sense. Often with the map function, but you can also write your own functions to kind of apply some sort of operation all the way across. So are we good on concepts? Are we getting a feel for functional programming? All right. So why would we want to use functional programming? And the first one is hopefully you're starting to see that a lot of these pure functions are a lot simpler to write. And of course, that means they're faster to write. And as we talked about earlier, pure functions will always work correctly because the inputs and the outputs will be accurate every time. Have any of you done like debugging in Java or some other language that gives you this obnoxiously huge stack trace of problems? And the problem might be at the top, but it might be somewhere in the middle of the stack trace too. It's generally a really big pain. But if you can do things functionally and you know which functions are really accurate and written correctly, it usually makes stack traces a lot easier because you can kind of look down and see like, well, this is the one where the database access happened. Maybe that would be the problem, or different things like that. So it usually helps with debugging as well. And type inferences can reduce these errors before they happen at runtime by finding them at compile time. And I think it's Elm that has these like beautiful error messages that say, this is your line, this is the exact problem in that line where the error is, and usually also even refers like an example of how to fix it. Like it's that precise because it's just that well designed. So if it's a functional language, it's usually built to be really accurate like that. And hopefully unit testing is functional programming because you sort of set up an environment, you run a function, and then you sort of destroy your environment. Since you're building that environment the same every time, your unit test should be accurate every single time. So no side effects should, in theory, happen if you're doing your unit test correctly. It's entirely possible to not do this correctly, but in theory, they're designed to be accurate that way. And of course, your global state of your program isn't affected by these pure functions. So you would want to do this just because like weird things aren't happening off on the side. Your variables aren't getting changed in other areas of your program, stuff like that. And this also means that your functions become parallelizable because they can kind of run on their own. They're not modifying other things. You can run them more than once at the same time. And you can run them in any order too. So you don't even have to call 1, then 2, then 3. You can just run 2 and then 1 and then 3. Or whatever order really works. So it kind of makes sort of larger operations work a lot nicer. And as your code grows larger, it also becomes more reliable overall. So these really better smaller modules make up a lot better larger modules. Okay, so I've thrown a lot at you in the last 20 minutes. Who's ready for a fun activity? I heard one yay. Good, okay. It's still early, right? Yeah. Okay. So activity 1 is here in a moment. I'm going to have everybody stand up if you're able to. So in the beginning, so far we would have counted 0 people. So we're going to start at 0. And then each person will go and increase that number by 1. So if I'm starting with person 0, and you're the first one, you would be 1, and then 2, and then so on. Say that number out loud, and then sit down. And then the next person will say the number and sit down. And so whoever's the last person in the room will report the total. Hopefully this is a pretty easy activity that I think you all can do really well. So who's up for it? Ooh, okay. All right, let's stand up. I guess we'll just go by rows. So I guess I'll start with you in the front row.
1.
And sit down.
2.
And sit down.
3.
Okay, and then
4. 5. 6. 7. 8. 9. 10.
you skipped a row.
13. 14. 15. 17.
There you go.
21. 22. 23. 24. 25. 26. 7. 28.
29,
30. 31. 34. 36. 37. 38. 39.
41, 42, 43,
44. 45. 46. 47.
Okay.
55,
56. 57. 58. 59. 60. 62. 64. 65. 67. 68. 69.
Cool. There's 70 people in the room. Cool. That'll be one for if anybody asks me later how many people, so I know. But no, there's a point to this activity, really. Okay. Who's ready for activity 2? Yeah. Ooh, y'all are awake now. Cool. All right. So in a moment, everybody's going to stand up again. So you are one person on your own. So your internal total is going to be 1. You're going to find a neighbor, and then you're going to add up your 2 numbers. So whatever your number is plus their number. One of you will sit down. I'll let you decide who wants to do that. And then we're going to repeat. So you're going to, whoever stays standing up is going to find another neighbor and add your 2 numbers together. And then one of you will sit down. So then in the end, I said an extra volunteer will just have whoever's left over should be able to tell me what that total is at the end. So one person will be standing up at the end. Does this make sense? Maybe. A lot more skeptical, right? Okay. Okay, stand up. All right. Does everybody remember what number you started with? Good. Okay, go find a neighbor. Sarah? Sarah?
I thought the twist of the last activity would be that the last person was not supposed to add 1 to the number. Because if you look at your algorithm, it says that people should add 1 to the number and then say that I will sit down. And then the last person should then announce the total. It doesn't say that the last person should add 1 to the total.
All right. I'll allow that. I'll work on that.
Just thought it'd be a different thing to think about.
All right. I think we're 3 people left. I feel sorry for you. You're just kind of like on your own there.
83.
83, and what was your number? 30. Oh, holy cow.
There's a bug in there.
Yes, apparently. All right, you can sit down. Or 30 people snuck in the room in the middle of this activity, right? Yeah. 40 people? 43 people? Anyway. Okay, so this is kind of a really, really silly way to do this. But the point was to try and show that activity 1 was really kind of a for-while loop. So each time you just added 1 to the number, and it took a really long time. In theory, activity 2 was sort of a recursive and concurrent way to do it. Since multiple groups were counting at the same time, it should have been a little faster. And in theory, this would have been kind of like reduced function across all the numbers in the room. That didn't quite work right, but that was kind of the basic idea. Yeah.
I have a suggestion. People are not pure.
People are not pure. You make a good point. I think we explained that in the beginning. User input's never pure. All right. But hopefully made kind of a point. So my friend Jessica Kerr had a functional programming talk, and she had this example, which she lets me use. But so if you were managing sort of a business that took in like a nonprofit kind of charity business that took in like financial donations as well as like item donations, you could kind of go through and see if there was a unused deposit amount. And then kind of in the next step, get any of those unused donations, sort of add them to the deposit. And each time you're creating like a link record in a database, and then check that, yes, we've marked their donation as donated by that person. And kind of in the end, you have this like full deposit that you can go send off to the bank, and then you kind of repeat this process. And this might be how we would do it in sort of a procedural or object-oriented kind of way. But we can kind of restructure it a little bit differently and say, okay, so we have all these deposits and we have all these donations. We can kind of filter by which one of those have been unused or not tracked yet. And then there, put them in together with a matching function, which would be, so the unused and the matching both could be pure functions because they would work the same every time. And then from there, you could match these things up and then store them in a database. And then mark them in another database, perhaps. So we kind of taken those sort of side effect routes where we don't know exactly where the data is coming from, don't know, the accuracy of it, and sort of pushing them out to the edge cases. And so we do all of our functional work in the middle, so we know it's a little bit more accurate that way. So writing these functional programs takes a little bit of a mindset change. There's not really a direct conversion from I do procedural or object-oriented to, this is functional. It takes a little bit of a thinking difference, but hopefully you can start to see you can do some functional style things in object-oriented programming, but you can also have functional stuff that uses objects in it as well. So they're not like a war where they're fighting against each other on which one's really better. You can actually have both at the same time. So kind of briefly, I want to wrap this up a bit by looking at different types of programming languages and kind of looking at which ones are actually purely function. And so this is the most pure functional languages I could actually find. So the languages built from the ground up being entirely functional. So has anybody heard of any of these languages? Yeah, there's a few in there. The list was actually smaller than I thought it would be because like I said, I did a project in Haskell once, but most of these other ones I hadn't really heard of. I think PureScript I had heard of, and then Elm, like I mentioned earlier, but there was a lot fewer than I thought. And then these are the impure functional languages. So these are languages that are not built from the ground up, but have functional concepts kind of built into them, like passing functions as arguments and things like that. So hopefully there's at least one language in here everybody's heard of. And probably the majority of you actually work in some language that's on this list. So most of these have, it's probably in different time variances, like C++ didn't have them in the beginning, but they had them after. C++11, for instance. One of the ones that surprised me was spreadsheets. I'd never really thought about it, but spreadsheets are functional because each cell kind of does its own thing, and you can pass in inputs from other cells, which I thought was kind of cool. I'd never really thought about it before. So hopefully this is kind of encouraging that you can maybe take some of these ideas and take them into wherever you work right now. Okay, so to kind of wrap up everything, functional programming, it's getting more popular, a lot more buzzwords, but it's really been kind of the solid concept that's been around for quite a while. Doing functional programming will make your code simpler, smaller, and usually a lot more reliable as well. And these can work in nearly any language at the point. So pretty much every common language uses these, and you can start using them today. So anybody going to run out and start using one like after the break? One person? Cool. No. Okay, you can do it when you get back to work, obviously. So anyway, thanks for coming. Hopefully you've learned a few new things from this. You can always find me online. You can email me at hello@sarahwithee.com, or you can find me on Twitter at geekygirlsarah, and I'll be around for the rest of the week. And all my slides are up at geekygirlsarah.com/primerfp. So thank you for coming. If you have any questions, you can come up and ask.